Hello, greetings of the day. Today I have come up with a collection of questions from work and energy so that you can summarize your concepts and see how these concepts are applied while solving a given physical situation. Let's get started.
Okay, let's start doing problems. The first problem we have, the two balls shown in figure are identical. The first moving at a speed v towards right and the second staying at rest. The ball at the extreme right is fixed. This ball B is fixed. Assume all collisions to be elastic. Show that the speeds of the balls remains unchanged after all the collisions have taken place. So we have to consider the cases till collisions are taking place. So let us start with the first collision. If I write for first collision, as the balls have equal mass and they are making elastic collision, so velocities has to be interchanged. Now after the first collision, the ball A will come to rest and ball B will start moving towards right with a speed v. So we can show the situation here. A has come to rest and B started moving with speed v towards right. Now it will collide with the wall and will come back with the same speed because again collision is elastic. If I consider second collision, this collision is between ball B and the wall, and this being elastic, B will come again with speed in opposite direction and the same magnitude. Now this is the position of B. A is still at rest. Now let us consider the third collision. Now this B is moving towards A and A is at rest. So again there will be elastic collision, both being of same mass. So B will come to rest and then A will start moving with the same speed v but towards left. After this collision, is there any possibility of further collisions? No, because A will continue moving towards left with this constant speed while B will remain at rest. So there are total 3 collisions here taking place in the system, and as I have shown that speeds are unchanged. Here it is written speed, not the velocity. You can see that for A, of course, velocity has changed. For initial moment, it had velocity towards right, and after all the collision has taken place, it has velocity v towards left. But speed has not changed. For B, initially also it was at rest, and after all the collisions also again it is at rest. So now this is proved that speed of the balls remain unchanged after all the collisions have taken place. Now let's move to next question. A block of mass m moving at a velocity v collides head-on with another block of mass 2m at rest. Here we have to consider this is velocity of mass m and the other ball which has mass 2m, it is at rest. If coefficient of restitution is 1/2, find the velocities of the blocks after the collision. Okay, let's first write momentum conservation. Here we can write before the collision, since second body 2m mass body is at rest, so we can write momentum before collision to be equal to mv. And after collision, let us consider one starts moving with velocity v1 and the other starts with moving velocity v2. So I have considered these direction for velocities of mass m and 2m after the collision has taken place. Now if we write momentum conservation, it will be mv is equal to mv1 plus 2mv2. This is our equation number 1, which is momentum conservation. Do remember, this time as coefficient of restitution is given 1/2, so it is not a pure elastic collision or even a pure inelastic collision. It is something for which coefficient of restitution has value between 0 and 1, that is equal to 1/2. So though we can write momentum conservation, we cannot write energy conservation here. But since coefficient of restitution is given, and what is coefficient of restitution? It is velocity of separation upon velocity of approach. So this we will write as v1 minus v2. Since initially 2 was at rest, so it will be 0 minus v. and this value is given as 1/2. So from here we can write V1 minus V2 is equal to minus V upon 2, or V2 minus V1 is equal to V by 2. On solving equations 1 and 2, we will get finally V1 will be equal to 0 and V2 will be equal to V by 2. So these are the final velocity of the blocks after collision taken place. What's the next question? A block of mass 1.2 kg moving at a speed of 20 cm per second collides head-on with a similar block kept at rest. The coefficient of restitution is 3/5. Find the loss of kinetic energy during the collision. Here again we can see that coefficient of restitution is given 3/5. So it cannot be a fully elastic or fully inelastic collision. Here also we cannot write conservation of kinetic energy. That's why it is asking for loss of kinetic energy. So let us start with again momentum conservation, because every time we can write momentum conservation. Before collision, momentum will be equal to 1.2 multiplied with, this is given 20 cm per second. Let it remain in this unit only. And after collision, if speed of this 1.2 kg mass is V1 and for other mass it is V2, then we can write 1.2 V1 plus 1.2 V2, because both are having the same mass. One was at rest and one was moving initially. So we got this expression which can be written as equation number 1. From here, as masses are same, so directly we will get V1 plus V2 to be equal to 20 cm per second. Now if we see what is velocity of separation, then V2 minus V1 is velocity of separation. This is velocity of body 2 with respect to 1. If we divide this velocity of separation by velocity of approach, that is equal to V, then it has to be equal to coefficient of restitution, and this value is 3/5. So we can write 5 V2 minus V1 is equal to 3V. One more equation we got. Now if we solve equation 2 and 3, we will get V1 to be equal to 4 cm per second. I had not converted initially the units for speed, so final also we will get in centimeter per second only. V1 we got as 4 cm per second and V2 16 cm per second. But it is asking for loss in kinetic energy. So loss, since it is asking, it has to be equal to initial kinetic energy minus final kinetic energy. This is initial minus final. If I substitute the values here, that will be equal to half. Now mass is given 1.2, so it is 1.2 and then square of speed, which is square of 20. Minus, we have to write again half into 1.2 into, this time speed of first body is 4, so it will be square of 4, which is 16, minus 1/2 into 1.2 into square of 16, which is 256. If we solve these values here, that will be equal to 7.7 into 10 to the power minus 3 joule. Here I have converted all the speeds to meter per second to get our final answer in joule. So far so good. Let's move to this next question. A ball of mass m hits the floor with a speed v, making an angle of incidence theta with the normal. The coefficient of restitution is E. Find the speed of the reflected ball and the angle of reflection of the ball. First, the ball is coming to strike the floor with speed v and making angle theta with vertical. After collision, it is moving away with speed v dash and making angle theta dash with normal. So let us see. Of course, we can write momentum conservation. But in which direction it should be written? So first, Consider that since there is no force parallel to the surface, then parallel component of velocity should remain unchanged because there is no force in this direction, so velocity cannot change in that particular direction. And we got from here v sine theta should be equal to v dash sine theta dash. This is our equation number 1. Now for the component normal to the floor, of course we have to write coefficient of restitution. So let's write that. E can be written as, it should be velocity along normal after the collision upon velocity along normal before the collision. So this will be equal to v dashed cos theta dashed upon v cos theta. This is our equation number 2. On solving 1 and 2, we will get finally v dash to be equal to v taken common sine square theta plus e square cos square theta. Also we can write, because it is asking for angle also, so we have to get that value, tan theta dashed is equal to tan theta upon e. We can see this from these two equations itself. If it had been an elastic collision, then E had been 1. Now this I am discussing which is not related to the given question. Let us consider if E is equal to 1. Then we could have written that theta dashed is equal to theta and v dashed is equal to v. So the ball would have reflected with the same speed and the same angle of reflection. So this theta and theta dashed v and v dashed would have been equal. This is the case when collision is fully elastic. Otherwise, according to the given question, it is our answer. Now let's see next question. A block of mass m and a pan of equal mass are connected by a string going over a smooth light pulley as shown here. As you can see, this is the pan of mass m on which a ball is coming to strike it. This also is having the same mass. It is coming down with speed v. Then we have to find the speed with which the system moves just after the collision. One more thing is there. On striking with the pan, the mass gets stick to it. So let us see how to solve this question. Now let us consider that after this collision has taken place, the speed of the system has become v dashed. The speed which is required here I have taken as v dashed. Now as there is a sudden change in speed of block, then tension also must change by a large amount during the collision. And what kind of force that is called? It is called an impulsive force. So if N is magnitude of contact force between the particle and T is tension, I have taken normal as N and tension as T, then we can write impulse momentum theorem here. So what it will be? Impulse imparted by N has to be equal to integration of N dt. And in what direction it will be? In upward direction, because normal is in upward direction. So this should be equal to change in momentum for the ball, because this impulse is imparted by pan on the ball. So it can be written as change in momentum we have to write, that will be equal to mv minus mv dashed. This is our equation number 1. Next we have to consider the impulse imparted to the pan. Now for pan, as you can see, it is attached to string also. So two impulses will be imparted, one by the tension and other by the normal. Because if it is exerting a force normal on the particle m, then particle m also will exert the same impulsive force n, but now in downward direction on the pan. So if we write for the pan, total impulse will be equal to n minus t. And you can see this is in downward direction and tension is in upward direction for the pan. So we have to write n minus t dt. Its integration, that is the total impulse for pan, and it has to be equal to mv dashed. This time I have written only mv dashed because initially the pan was at rest. Now if we solve these two equations, we will get impulse due to normal to be equal to 2mv dashed. And we can write mv minus mv dashed is equal to 2mv dashed, which is from equation number 1 I have written. This is our equation number 3. On solving this, we will get finally v dash to be equal to v upon 3, which is the desired speed the system gets after particle has stuck to the pan after colliding with it. So this is our desired result. Now one question I have taken, though it is not related to collision, but these kinds of questions you will get in JEE and in Neet exam as well. So let us see how to solve these questions, because whenever two blocks are connected with a spring, the question becomes a little difficult than it had been with only one block. So let us see how these kinds of questions can be solved. Here a light spring of constant K is kept compressed between two blocks of masses M and capital M on a smooth horizontal surface. When released, the blocks acquire velocities in opposite directions because it was originally compressed. So after being released, the spring will try to come in its original length and both the blocks will be pushed apart. The spring loses contact with the blocks when it acquires natural length, which is quite obvious. If the spring was initially compressed through a distance d, then we have to calculate final speeds of the two blocks, and it should be the moment when the blocks are losing contact with the spring. So let's see how to solve this question. As no external force is acting on the system in horizontal direction, so we can write linear momentum to be constant. Also, as the spring is light, so it has no linear momentum. Now let us consider the block of mass m moves with a speed capital V and small m moving with a speed small v after losing contact with the spring. Now as the blocks are released from rest, so initial momentum has to be 0. Now we can write momentum conservation in horizontal direction, and initial momentum we have got is 0. This has to be equal to final momentum. Now what is the final momentum? It is equal to mv for the block of mass capital M minus mv, because they are moving in opposite direction, so we have to put a minus sign here. This is our equation number 1. Initially energy of system is, it is equal to half, initial compression is d, so that is equal to half k d square, and final energy, this is initial energy. Of course, final energy will be equal to kinetic energy of both the blocks, that has to be half mv square plus half mv square. This time, since spring has come to its natural length, so no energy remains stored in it. Now if we equate these two energies, we will get half kd square is equal to half mv square plus half mv square. On solving these two equations 1 and 2, we will get mv square, if taken common, 1 plus m upon m is equal to kd square. From here we can write v is equal to under root km upon m, and then in bracket it has to be m plus m. This multiplied with d. Also, speed of this bigger block, that is of mass capital M, can be written as km upon m multiplied with m plus m d. So these are the velocities of the blocks after the spring has come to its natural length. One more question is there from the spring mass system. A block of mass m is connected to another block of mass capital M by a massless spring of spring constant K. The blocks are kept on a smooth horizontal plane. There is no friction to be considered. Initially, these are at rest and the spring is unstressed. Now, a constant force F starts acting on the block of mass capital M to pull it. Find the maximum extension of the spring. See, when both the ends are free and the blocks are connected with a single spring, always it will be easier to solve the question in frame of center of mass, because both blocks will not be having the same velocity at a given time. They may have different velocities, so it will be easier to solve if we solve in the frame of center of mass. So let us see how it can be done. Now if we consider these two blocks plus the spring as the system, the center of mass of the system will move with acceleration. For this whole system I am writing, so acceleration has to be equal to F upon m plus m. This is acceleration of center of mass of the system. Now if we have to work from this reference frame in the frame of center of mass, then it is accelerated frame, so it is a non-inertial frame. And since we are writing equations in non-inertial frame, so pseudo forces are to be applied. Let us write for this block which is having mass capital M, what forces are there. This is the external force and then one pseudo force. Now pseudo force has to be in the direction because it is the direction of acceleration for center of mass. So it has to be in this direction, and magnitude will be equal to mass multiplied with acceleration of frame, that is acceleration of center of mass. So net external force if we write for this block, that will be equal to F minus MA. And if I substitute the value of A from above, this will be equal to F minus MF upon M plus M. That is equal to MF upon M plus M towards right. Now from this frame, since center of mass is at rest in its own frame, so the blocks will move in opposite directions and come to instantaneous rest at some instant. The extension of spring will be maximum at that instant only. I had said this earlier also. Whenever maximum compression or maximum extension has to be there, then relative velocity of both the ends has to be 0. So both will come to a momentary stop, we can say. And then we can write total work done by external forces F1 and F2 in this period to be equal to work done. If I write F1 x1, here I am considering that block M with capital M mass has been displaced by x1, and for other block this is x2. So it can be written as the total work done will be F1 x1 plus F2 x2, where F1 and F2 are external forces on the blocks. This will be equal to MF upon M plus M x1 plus x2. So now we can write this work done to be equal to the energy stored in the spring. So it can be written as MF upon M plus M x1 plus x2 to be equal to half K x1 plus x2 whole square. And on solving it will give x1 plus x2 is equal to 2mf upon K M plus M. This is the maximum extension possible in the spring. So this is the way in which a question has to be solved if it involves of a spring attached to two blocks and both the blocks are free to move. I hope you understood all the concepts that had been taught today. Just keep practicing more and more number of numericals. Goodbye.